Okay, this is part 2 for chapter 18 on blood. Last time we talked about blood typing. We're going to cover 2 of the typing systems that we encounter. So we're looking at the ABO blood typing system. It's a genetically controlled system that identifies agglutinogens A and B on surfaces of the erythrocytes. Oops. The body also produces antigen or antibodies, agglutinins, in the plasma. Now, here we see the distinctions of A, B, AB, and O. The type is identified with the agglutinogen present. So type A means you have the antigen or agglutinogen A present, but it also means that you produce the antibodies or agglutinin B. Genetically, that means that you're either going to have 2 dominant genes or you're going to have a dominant gene and a recessive gene. If you have type B blood, you have the B antigen and you make the antibody A. Again, genetically, you can have 2 dominant genes, one from mom, one from dad, or you can have a dominant gene and a recessive gene. Okay, if you have type AB blood, that means you have both A and B antigens, but you don't make any antibodies. So that means you have to have the genetic trait for A and the genetic trait for B. There's no other possible genetic combination. Now, what this means is that with AB blood, since they don't make any antibodies, then they can be given any type of blood in this system. If you have type O blood, that means you have no antigens, but you make antibody A and you make antibody B. So that means that you have 2 recessive traits. It also means that that's the only kind of blood that you can receive because you have both antibodies in your body. You can make them. And so every time you get exposed to one of the agglutinogens, you're going to react. It also means that O can be given to any of the others because there are no antigens present on the erythrocytes. So they're not going to trigger a response. So one blood typing system, ABO for the possible combinations. Again, it's related to a single monosaccharide on the glycocalyx. Either this one or this one. This shows AB where they have both. Type O blood doesn't have any. It doesn't include a representation of the antibodies. A second type typing system, is the RH type system. Here, it's genetically controlled. There are only two possibilities. Now, this system includes agglutinogen C, D, and E, but the only one that causes a problem is D. So you have Rh positive and you have Rh negative. Rh positive means that you have, in addition to your ABO, whatever that is, you have an agglutinogen D on the surface of the erythrocytes. This is more common as it's dominant. So with Rh, you could either have the Rh positive gene twice, one from each parent, or you could have the dominant gene and a recessive gene. With Rh negative, it means you have the potential to produce the agglutinin or antibody, but only if you're exposed. So you can make the antibody, but you don't automatically do it. This is less common. You have to have two recessive traits to become Rh negative. So we typically talk about being A positive, O negative. So those are two different systems of typing blood, two different compounds, two different materials within the blood. So because Rh negative doesn't have any agglutinogens, or it doesn't have agglutinogen D, that means that negative can be given to anyone. So if they don't know what your blood type is, you're going to get O positive, or sorry, O negative. And that is why people with O negative blood are hounded by the Red Cross, because that can be given to anybody if they don't know what your blood type is. Okay, another aspect of this Rh blood typing system is the condition of erythroblastosis fetalis. It occurs with an Rh negative mom. Where are we at here? Rh negative mom and an Rh positive dad. So no other grouping is going to get this problem. The first Rh positive fetus exposes mom to the agglutinogen or antigen D, causing her to make the antibody D. Any subsequent Rh positive fetuses are going to be attacked by those antibodies or agglutinins. To stop mom from making those antibodies, an injection can be given called RhoGAM. It's given at the beginning and the end of known pregnancies to stop mom from making the antibodies. So if a woman is Rh negative, she has to be careful. Unless she knows dad's or the sperm donor's blood type, there has to be some precautions taken against her body attacking her fetuses. The RhoGAM is a gamma globulin injection. So any Rh negative fetuses would be fine. Rh negative fetuses, Rh negative fetuses are going to be fine. It's the Rh positives. So if all she ever has is Rh negatives, then she doesn't need the shot. But with Rh positive fetuses, that's going to cause problem. And nothing happens to the first Rh positive fetus, it's the subsequent ones. Erythroblastosis fetalis. Okay. Another group of formed elements are the leukocytes or white blood cells. Leukocytes are large nucleated cells involved with immune activities. These cells can last anywhere from a few hours to several years, decades. We put them into two groups, whether or not they have clumps of proteins in their cytoplasm. Granulations are the clumps. You see them in 3 of the types of leukocytes. Those are called granular leukocytes. We also call them granulocytes. The agranular ones don't have this granulations in the cytoplasm, so they are agranular or agranulocytes. You have a table that will fill out for the individual leukocytes in the columns. The first one is going to be neutrophils. They're granular. They account for 60 to 70% of leukocytes. Their function is that they are phagocytes that can also secrete antimicrobial substances. Note that they end in "phil." All of the granular leukocytes are going to end in "phil." Eosinophils, this one here in the middle, is granular. It accounts for 2 to 4% of the leukocytes, and they deal with parasitic worms, allergenic proteins, and diseases of the spleen and the nervous system. So if you're having an allergic reaction, if you've been infected with a parasitic worm, these are going to be increasing in number. Basophils are granular. They have the most numerous granulations of the 3. They account for less than 1% of leukocytes. They secrete 2 chemicals, histamine and heparin. Histamine is a vasodilator, meaning that it's going to cause the blood vessels to make their lumen bigger. It increases blood flow. It's why we get watery eyes, runny nose, swelling around an infected cut, redness in that cut. So it increases blood flow. Heparin, on the other hand, is an anticoagulant, meaning that it helps keeps the blood in a liquid state. It stops it or reduces the likelihood of coagulation taking place or clotting. Heparin is used to keep intravenous lines open to reduce the formation of clots. Like say if you're in a hospital bed for an extended period of time, they can give you heparin shots to reduce the likelihood of developing a clot since your activity level has diminished. So again, if they end in "phil," they're granular. Then we have lymphocytes, which are agranular. That's what we see here. They account for 25 to 33% of all leukocytes, and they carry out various immune activities. In the lymphatic chapter, we talked about T cells and B cells. So you can refer back to those notes for the specific actions of different lymphocytes. Now, when we look at the lymphocyte, physically, we can't just, in a microscope anyway, tell the difference between a T cell and a B cell. We have to have a biochemical assay of what's present, and then we can look and tell what kind of specific lymphocyte it is. Monocytes are also agranular. They account for 3 to 8% of leukocytes, and they're large phagocytes. They gobble up smaller cells, smaller pathogens to consume them. These bright red things are the erythrocytes. And so they are going to be the most numerous formed element. The purplish stain comes from stain applied to the leukocytes. So if it's agranular, it ends in CYTE cell. The third group of formed elements are the platelets. They're tiny fragments of a megakaryocyte. They secrete platelet factors 1 through 4, so 4 different chemicals, and they're involved in hemostasis and coagulation. They can last 5 or 6 days in circulating blood, and they tend to aggregate or collect in the spleen until they're needed. So what we see here, drawn to size, is a megakaryocyte in the bone marrow. And what it does is it creates an extension that goes into blood vessels. And those extensions are going to break off into teeny tiny little pieces called platelets. So big chunks, not a platelet, teeny tiny little things, platelets. So they're not a cell, neither are erythrocytes in circulating blood. All right, hemostasis and coagulation. Hemostasis is a series of actions that follow damage to a blood vessel, which is what we see here, to reduce blood loss and reduce blood flow. So your textbook has a picture where they cut the whole blood vessel. This shows a puncture wound, and I like it better. So that's why I kept it. There are 3 steps. They each have their own name for hemostasis. Hemostasis involves a vascular spasm. The smooth muscle tissue is going to contract in order to narrow the opening to reduce blood flow. So vascular for blood, and then spasm, it's the smooth muscle tissue in the lining of the blood vessel that's going to contract. Step number 2 involves plugging up the opening with platelets. So a platelet plug is produced or formed by piling the platelets into the opening, again, to reduce blood loss. The third step is called coagulation or clotting. It finishes off by sealing off the area and stopping the loss of blood. So it's going to glue together, forms proteins that glue together the platelets into a solid mass. Three steps in hemostasis. So looking at just coagulation, there are two kinds of coagulation, extrinsic and intrinsic. Extrinsic, which is this green box over here, is triggered by damage to a blood vessel and is part of hemostasis. And that's what we looked at just on the previous slides. Intrinsic coagulation is the purple. It's triggered by foreign surfaces, compression of a blood vessel, and or pooling of blood, lack of movement. So with intrinsic, something inside the blood vessel gets irritated. Like I said, if you compress, like if you wear clothing that's too tight, or if you don't release the pressure on a blood pressure cuff soon enough or quickly enough, pooling of blood, not staying in the same position for extended periods of time, which is why you're supposed to turn patients every 2 hours. Okay, so you have two different ways to start the process of coagulation, and then you have a single pathway that it follows. The clotting factors are the compounds involved in producing a clot. So the liver and the platelets produce and release these clotting factors. We need to make the ultimate glue, which is the fibrin polymer. Examples of clotting factors include prothrombin and fibrinogen, which we've already talked about, anti-hemophiliac factors A, B, and C, the platelet factors 1, 2, 3, and 4, and several others like Hageman factor. You have a table towards the end of chapter 18 that lists the clotting factors. Now, in that table, they get distinguished with Roman numerals. So clotting factors 1, 2, 3. Now, that list is incomplete because some things they thought were part of the process were not. And so they took them off the list. But for some reason, people still kept using those numbers. The red things that you see in this picture are platelets. The white things are the fibrin polymers. So fibrin polymers act like a glue. All right, and yes, you need 2 or 4 examples, a total of 4. 2 of them need to be something other than prothrombin and fibrinogen. Okay, in addition to the clotting factors, you also need calcium ions for several of the chemical reactions. So this is not a clotting factor. These are additional materials. Also, we have to have vitamin K. Now, vitamin K is a building block to make several of the clotting factors. These are secreted by bacteria in our colon. So when we eat solid foods, we acquire bacteria in our colon, and they produce vitamin K. There are foods that have vitamin K. If someone's on an anticoagulant, they have to watch their vitamin K consumption because that can throw things off and be counterproductive to the anticoagulant they're taking. One of the things that was on my mom's list, and it was the one thing that made her irritated, was licorice. Yeah, talk about being pissed off. She didn't have she doesn't like giving up lettuce or other green leafy vegetables, but she did have a problem giving up licorice. Okay, so the common pathway is what you have to memorize. First step in the common pathway, factor 10 is activated by either the intrinsic or the extrinsic mechanism. That's going to combine with factors 3 and 5, as well as calcium ions and platelet factor 3. All of that produces the compound prothrombin activator. So factor 10 combines with factors 3 and 5, as well as calcium ions and platelet factor 3. Once we have prothrombin activator, then we can move on to the second step. Prothrombin activator, along with factor 5, another molecule, is going to convert prothrombin into thrombin. So it activates it. It's kind of like a stamp that on the back is dried glue and you lick it so that it activates it. All right. So with thrombin's going to combine with, thrombin is going to combine with fibrinogen to form fibrin. Fibrin then combines with factor 13, another calcium ion, and that's when it makes fibrin polymer. Now, one other thing back here. Once you have prothrombin activator, you can reuse that. So as long as you have enough factor 5 and prothrombin, this creates a positive feedway path that doesn't have to go back to the beginning. Once we have fibrin polymer, it's going to glue the platelets and anything else into a clot, which is what we see here. So that should have filled in all of your blanks. All right, so that's the end of chapter 18 on blood.